just not quite as close as I would have liked. So we'll go through kind of the electrophilic aromatic substitution reaction, general concepts, what's happening on it, simplifications, things that you can kind of adjust to help you get through the material a little bit faster, hopefully. Okay? So the first thing we'll do is break down the definitions. Electrophilic, we're looking at something that is electron-loving. If we can come up with a symbol, what kind of symbol might be a good idea for an electron-loving species? I can accept a heart. I can do that. I can probably even draw that. A heart with a positive charge. Okay, so we've got our electron-loving species. It's going to be positive. Why does it have to be positive?
Because it attracts negative.
It has to be attracted to the negative. Okay, so we've got our electrophilic species, and then we've got aromatic, which, as far as you guys are going to be concerned, pretty sure for the rest of the semester, we're going to look at benzene. Okay, so we could draw out a structure for benzene. What does that end up looking like? Right, so we've got our aromatic ring. The very last thing says substitution, which is going to imply a reaction, right? So we can throw in an arrow. And we're going to have to, oh, this is going to get interesting. So the substitution reaction means we're going to swap something for another. Okay, well, we've got two pieces here. Our benzene has what in it? What atoms are in a structure of benzene? Carbon and hydrogen. So we've got C6H6, right? Which of those is going to be the easiest to substitute for? Carbon or hydrogen? Hydrogen. Why the hydrogen? It's only got one bond. It's the easiest one to get access to. So that's the one we're going to end up substituting for. So if we're going to have to draw out the product, thanks for the heart, by the way. What's our product going to look like? We're going to have our benzene ring, except instead of having a hydrogen on there, we're going to have a heart.
Just completely degrading this lecture again.
That looks like a heart.
I didn't think you'd take me seriously.
So we now have our substitution reaction. And ultimately, this is what you should be looking at. You should be recognizing that atoms, or the symbols that we use for atoms, just happen to be the easiest thing for us to draw out. That's why we use letters. It could have been very well symbols. We could go through and draw our reactions using symbols, the exact same idea. So it doesn't matter necessarily that we use a heart versus letters. The only reason we pick letters is most people can draw out letters better than they can draw out hearts, as we can clearly see. Okay, so now that we've got an idea of what's happening with the overall reaction, we can kind of start to evaluate what's happening here. Okay, so what we're going to have to do is go through and identify the individual pieces here. Our electrophile, I came up with the symbol that I thought you were going to pick instead. E might be a nice symbol for an electrophile. It's still going to be positively charged. Okay, so that is going to be our reactive species. What does that make our benzene ring then? Electrophiles tend to react with nucleophiles. What's our definition of a nucleophile? It's a nucleus-loving. What is it going to have to supply? Electrons. So we can look into our aromatic system and try and find the most reactive electrons. Where are the most reactive electrons in that structure? So we could look at the electrons between the hydrogen and the carbon. What type of bond is there? It's a sigma bond. Okay, we're looking at direct overlap of those two orbitals to generate that bond. Okay, so those electrons are embedded between two atoms. How about the pi bond? How do we generate a pi bond? You take leftover p orbitals and you line them up next to each other. So let's attempt to do it this way with my forearms. So a sigma bond is direct overlap. A pi bond is indirect overlap. We've got those pi bonds near each other, and they're close enough that the electrons can jump back and forth. Where are the atoms, if you had to choose where the atoms would be? In between what? You got the right idea?
The pi bonds. The two.
So right in the middle of my forearm, right? A little higher? You want it higher? So it's somewhere in between those two places. So if we look at the electrons are on the outside. If we look at our sigma bond, the center of our atoms in this case could be my elbows. Okay? Those electrons are embedded in between the two atoms. When we move to the pi bond, where are the electrons? They're outside. Which of those electrons is more accessible? Something that's outside the structure or something that's within the structure? Outside the structure. So what we're looking at is the pi system of our benzene ring, and that's going to be the electrons that are going to donate out. And yes, that is not ultimately what happens in our reaction. So what we're going to have to do is evaluate what changes to our structure and what things we can alter as we get through this. So we can take our electrons and we will share them with our electrophile. The result of that is we end up changing the pi system. Okay, and we can put the electrophile on one of those carbons. What happens to the other carbon, in this case the bottom carbon? Charged. Which charge? Should it be positive or negative?
Positive.
It should be positive. Why should it be positive?
Because you took electrons away to
Exactly
make the...
right. We took electrons in that pi bond and we took them and made a sigma bond somewhere else. So our top carbon didn't really lose any electrons. We just shifted where its electrons were located. But if we look at that bottom carbon, it absolutely lost electrons. We took those away to make the sigma bond, which means that carbon that started neutral and lost electrons has now become positive. Is that structure stable? Okay, no. Couple reasons. What might be the easier reason? Okay, it has a charge. What's another reason? Is that our product? No. So something else has to happen anyway to get to our product. Okay, so we know this reaction occurs. We have to come up with some way to show it. Okay, so one thing for sure, it's positively charged. Let's stabilize that positive charge as best we can. Okay, how do you stabilize a positive charge? You give it electrons. Where's the most available electrons in this structure? Okay, so ultimately the exact same question that I asked earlier when we looked at our first step. Where were the most available electrons in our first step? In the pi bond. Okay, that's why the pi bond went out and attacked. Where are most available electrons now? Pi bonds or sigma bonds?
No.
They're still in the pi system. Okay? So what we'll do is look at the electrons in that pi system and see what we can do to stabilize. So what we can do is take those electrons, go ahead and change the color up on this, and we'll shift them over. Okay? What does that end up generating? We end up with this. I'm going to make this too big to fit on the screen. Bond. Okay. We haven't changed our electrophile position, so we'll leave that alone. What happened to that carbon there? It's now positively charged. Why? It lost those electrons. What changed as I moved between these two structures? Okay, symmetry. Okay, so that symmetry is nice. So we could look at a symmetry effect of stability, but that's going to be relatively minor. All we've moved in this case are the electrons. What have we drawn if the only thing we've moved around are electrons? Resonance. So what we can do is include our double arrow to show resonance. Okay. What we can do is again move our electrons. It's not officially back in this case, but you got the right idea. Ooh, let's try that again. That just looks like a circle. And we end up with what we would technically refer to as a new resonance structure. Okay. And ultimately what we've done is push that positive charge around the ring. So that's nice. We've stabilized the positive charge. But it's still positive. It's still reactive. We need to come up with a more permanent solution. Okay? So now instead of going into the pi system, we're going to have to find another source of electrons, which is where you all wanted to go initially, and I stopped you. Okay? And we said the sigma bond, and we'll look at the bond between the hydrogen and the carbon. Okay? So what we can do is take a look at those electrons. Which atom is more electronegative, hydrogen or carbon? It's not by a lot, but carbon is slightly more electronegative, which means the electrons in that bond spend most of their time on that side of it. We've got a positive charge that needs to get stabilized by bringing electrons towards it. So what we can do is take the electrons out of that bond and put it back into the pi system. And what we end up forming there's our electrophile. What happened to the hydrogen? We can't take the atom into the bond. The bond between the carbon and hydrogen, you're absolutely right. We took the bond out. But what happened to the hydrogen? It's still there. It becomes positively charged, so it could end up becoming another electrophile if you wanted. We wouldn't classify it as an electrophile because we could better classify it as a Bronsted-Lowry acid proton donor. Okay? So what we've got within this mechanism is several steps to go through and stabilize each of these things. Okay? If we take a look right through the middle of this, or right through the heart of our reaction, what I'm now putting in brackets, okay, what we've got happening in there is a resonance stabilized intermediate. So it's one of the things that allows for this reaction to even occur. Okay? When we start with our aromatic structure, those pi bonds all interact with each other and become super, super stable. To start this reaction off, we destroy that aromaticity, which is a bad thing to do. Okay? To regain our structure, we end up regaining our aromaticity, and we do our final substitution. Those three structures in the middle get a special name beyond just resonance. Any ideas? What type of bond is around this carbon? What kind of bonds does that carbon have that's different from all the others?
Could you repeat that? Sorry.
Take a look at the now highlighted carbon atom in green. Okay. In all three of those structures, what types of bonds does that carbon atom have? They're all single bonds. Single bonds get a special name, sigma. So what we're looking at is the sigma structures, okay? Because that carbon has that sigma characteristic that none of the other atoms have. Okay? So you might see those referred to as sigma structures, and in fact you will when we move into the lab. Okay? So, as with all reactions, we always want to make things go faster and higher yields. We had two species involved in our reaction. We had our electrophile, and then we technically had our nucleophile, which was the aromatic ring. Okay? To make something react faster, we need to make it more unstable. Our electrophile was unstable because it was positively charged. Okay, so how can we make an electrophile more electrophilic or more reactive? We make it a larger positive. Okay, so we have to somehow tweak and change the structure to make it more positive. Okay, so let's take a look at these three electrophiles. Which of those might you predict to be the most electrophilic? Left, right, middle. Okay, why the middle being the most electrophilic? Because you see a positive charge on it. Okay? So we would say that that nitrogen is extremely electrophilic. Okay? Between the other two, left and right, which one do you think is more electrophilic? Okay, I heard a right. Why do you say right? Which atom? Let's try that. Which atom in the rightmost structure is the most electrophilic? What do we know about chlorine? Highly electronegative, which means what does it do to the electrons and bonds near it? Pulls them closer towards itself. If it gains electrons, what charge does it start to become?
Negative.
Negative. So that's the opposite of what we're looking at. Where is it taking those electrons from?
Carbon.
What happens to the carbon? It becomes partially positive. So in that last structure, what we're looking at is that carbon being fairly electrophilic. So we've got that chlorine there, but do we have something else on that carbon as well that can draw electron density away from it? Say an oxygen, which is also extremely electronegative. Okay? So that carbon is a pretty good electrophile. Okay? If we move to the leftmost, bromine can act as an electrophile. It's kind of a tricky one to act as an electrophile, but it does work. And the biggest reason is that it is so large. The bromine atoms are so large, the electron clouds can be displaced enough that you can generate some partial positive charge, a temporary positive charge, which it can be maintained for long enough that you can get a reaction to occur. Okay? But let's see if there's something else that we could do to this structure. Let's see. Do I have another slide on this? Okay. Can we add something to make them even more electrophilic? We're ultimately trying to make those atoms more positive. Okay. What things do we typically add to a reaction to make it go faster? We could add a catalyst. Okay. That catalyst has to somehow pull electron density away from each of these electrophiles. Okay. So what we can do is add, say, a metal. Let's add iron tribromide. What can you tell me about iron? A metal is a valid answer, by the way. I heard someone say that, kind of whisper it. It is a metal. What do we know about metals? What's their charge typically? Positively charged. If something's positively charged, what might it like to attract towards it? Electrons. Do we have electrons conveniently drawn closely to this iron? We can take these electrons from bromine and coordinate them with that iron atom. Okay? Does bromine want to have multiple bonds? Bromine's one of the halogens, and our halogens all like to have single bonds, just one bond. So in this case, we're starting to form two bonds to bromine. So what does that bromine atom start to do? It's going to have to try and grab electrons from somewhere. Best source would be the bromine right next to it. What happens to that tail bromine? I don't even quite want to get to break off yet, but you got the right idea. Bromine started neutral. That last one, our boxed in bromine, started neutral. What happened to the electrons in the bond between the other bromine? Where did those electrons start to go? Towards it or away from it? Away from it, which means that bromine is now losing electrons. If a bromine atom loses electrons, what happens to its charge? It becomes positive. Iron tribromide acts as a catalyst because what it'll do is further polarize that bond in Br2, making one of those bromines extremely electrophilic and a lot more reactive. Okay? So what you can do is look at the character of your catalyst to try and decide what that catalyst is doing. Okay? How does it interact with the other molecules? Find electrons, find charges. Okay? It allows you to do a lot of prediction without knowing a whole lot. Okay? And if you're like me, that's how you pass. Okay? So let's take a look at how we could change the other half. That's looking at the electrophile. Let's look at the nucleophile. Okay? So in this case, the nucleophile is your aromatic ring. So we could go ahead and take a look at our 0 case, which is just standard benzene. Okay? If I want it to act as a nucleophile, what do I need to do? It needs more electrons. So we could try and add a catalyst that pushes more electrons into that ring. Except, what's the octet for all of those carbons? Are they satisfied? Can carbon expand its octet? No. So what does that mean? If I add a catalyst, can that catalyst dump more electrons into the carbon atom? No. So a catalyst doesn't help us in this case. We're going to have to somehow change the structure And by changing the structure, hope we can put more electron density into it. And that's what's happening in the two cases that we're looking at here, above and below. What changed when we moved from our center benzene ring to the top one? What have we added to our structure? We're going to swap, okay, or substitute an atom X. What's different about atom X? Anybody see a difference between atom X and our hydrogen atom? It has more electrons than hydrogen. If we look at atom X down below, what changed? So it has less electrons than the hydrogen. How does that affect our reaction? Well, what we can go through and do is everybody's favorite thing is draw out resonance structures. Okay? To start with resonance, we need to find a source of electrons. Okay? So we can move for our top one, because it's typically easier to look at that one. Because where's a nice easy source of electrons in that top structure? Atom X, because there's a lone pair there. So let's take that lone pair and share it downwards. Okay? How many bonds would then be to that carbon? 5. That's a problem. So what do we do with resonance? We're going to have to break a pi bond. Do we have a pi bond easily accessible to that carbon? Yes. So we're going to take that pi bond electron or electrons, and we're going to push them to the atom next door. Okay? And that's going to give us a resulting structure. What does that structure look like? Well, this is where it becomes helpful to have an ability to draw faster than I can right now, apparently. Okay, what happened to atom X? Lost electrons. It started neutral, so it's now positive. What happened to that carbon now? The carbon that was in that double bond. Has what? I just didn't hear you.
It has 4 bonds instead of 5.
We didn't actually make a new bond. Okay, because if we made a new bond, this wouldn't be resonance. Okay, so we took those pi electrons, we moved them from the bond, and where did I show those electrons going to? To the atom. So what did that atom just do? Gained electrons. It started neutral, gains electrons, so it's now negatively charged. Why is that important? Well, we were looking to find our nucleophile. What did the nucleophile need to have? Needed to have more electrons. What did we just do? We drew a resonance structure that put negative charge on the ring. Do we have that negative charge easily accessible in our hydrogen case? No. So what have we done? We've activated the ring. It has electron density. We've made our nucleophile more nucleophilic. By changing the atom on that ring, on the benzene ring, from a hydrogen to some atom that has extra electrons, I can speed up my reaction. Okay? What happens if we look at atom X where it has less electrons? So let's look at the other case. What happens in this case? We need to find our electrons to do resonance. Where are our electrons? Pi bond. So let's take our pi bond electrons and move them towards some place that lacks them. The one place that's lacking them, positive charge. Okay, so let's move it towards that positive charge. What's our result in that case? Good call. We make atom X neutral. Okay, that's not a bad idea or a bad thing. What happened to the ring? What happened to that carbon? Why is it positively charged? You're right. It lost electrons. What does that say about the speed or the nucleophilicity of this new structure? Should it be more nucleophilic? It should be lower because we don't have the electron density to attack. Okay? So by looking at the resonance structures, you can find out what's happening with the reaction and start to predict things. You should be able to go through and draw out the rest of the resonance structures for each of these cases and There's a couple conclusions that you can come out of this. So first off, for that atom X having more electrons than hydrogen, I left off the hydrogen. Let's add that hydrogen. Okay, that species reacted faster. Okay, we've activated our ring. We've made it a better nucleophile, so we'll call it an activator. For the bottom one, what did we do? We took electrons away from the ring. We've slowed the reaction down. So we can call it a downer, right? Haha, never mind. I thought it was funny. We can call it a deactivator. Okay? The other thing that we can go through and do, which you'll see in lecture, is for each of these species, we can also predict where the electrophile is going to go. In the case of the activator, where did I put negative charge? On the carbon. Which carbon? One on the left. Good call. So we could say the one on the left, but what happens if I pick up the structure and flip it over? Still on that same carbon. So we need to come up with a way to locate it. Okay, we could call it 6. That works. And by doing that, what are you suggesting? You're going to number the ring. 1, come on. 1, 2, 3, 4, 5, 6. Is that what you're suggesting? Okay, perfectly valid. So we've got negative charge at position 6. So we could expect our electrophile to add to or substitute at position 6. Okay, so we could go through, and what you'll end up finding when you draw out all your resonance structures is that positions 2, 4, and 6 are all activated. Okay, so we could say 2, 4, and 6 director. Our electrophile is directed to those positions. Okay, chemists don't like numbers, right? So what do we come up with?
Symbols.
Ortho and para, in this case, will come back to meta. Chemists don't like words, as you can tell by how often I speak. We jump to O and P. Okay. What? Oh, shoot. Darn it. I can't really bracket that as neatly, can I? So 4 is para. Sorry about that. I should have grouped that better to begin with. 2 and 6 are your ortho positions, and 4 is para. Okay? What happens in the case of the deactivator? Would I expect position 6, as we've got it numbered, to be activated? No. Why? There's positive charge. What did I need? It needed to be negative. What we'll find with the deactivating groups, as positions 2, 4, and 6 all build positive charge, can those parts of the ring act as or have a reaction with an electrophile? No, they're positive. Positive charges repel. So what ends up happening? The only thing that's left over is that last position, which is positions 3 and 5. Does that show up? Good. Again, with our dislike of names, we come up with meta or M. Okay? And if you think, well, there's no electron density there, it's true. That's why we call it a deactivator. There's not a lot of electron density there to begin with. That's why the reaction goes that much slower. But that is the only position on the ring that can actually donate any electrons. Okay? Kind of makes sense? Okay. So as far as your experiment goes, you're going to take bromobenzene. You're going to react it with nitric acid and sulfuric acid. In the process of that reaction, you're going to end up putting a nitro group, so an NO2. Sorry, let's try that again. An NO2 onto the ring. Okay? You'll notice that that line is going through the middle of the benzene ring, and that's because I'm not telling you where the nitro goes. Part of this experiment is to figure out and predict where you think that nitro group should go. Okay? Couple extra things to note. Nitric acid and sulfuric acid. Any primary concerns about those? They're very toxic, particularly your primary concern would be burns, chemical burns. They're very, very corrosive. Okay? They will also react with each other to give you your electrophile. Okay? okay, which is what's happening in the formation of the nitronium ion. Okay, so if we go through and look at this reaction, which I'll just draw out, and if you've got questions about it, you can ask. Your oxygen will donate electrons to a hydrogen atom. So H2SO4 will act as an acid. What does the nitric acid act as? Shared its electrons with a hydrogen. Nitric acid acts as a base in this case. Why? Because it's a weaker acid than sulfuric acid. And the process of doing this, I'm not going to draw on all the lone pairs because that takes a lot of time. Does oxygen want to be positive? Nope. So what's it going to want to do? Right idea, wrong direction. Take electrons. Which then means that nitrogen's really upset, so it starts to borrow electrons from the oxygen nearby. And we end up with our final product, H2O and nitronium. There's your electrophile underneath the sign. Dang it. Let me draw it above the sign. There's your electrophile. We can see that now, right? Okay. You need to be aware of what those species are acting as and how those arrows move. You will be tested on that. It shows up in all sorts of questions elsewhere. Okay? As far as your experimental breakdown goes, get your chemicals, get those out, build the reflux apparatus, and watch for the reflux. There's two big things that you can look for this reaction. Reflux is that you're forming gas or vapors that then condense and drip back down into the reaction. The other big red flag for this reaction actually functioning is the formation of a brown gas. That brown gas is some nitrogen oxide compound, also known as smog. Okay, so the brown dust cloud you typically see over Phoenix, a lot of that is due to some species like this. Okay, except now it's super concentrated in your reaction. Please do not breathe that. Keep it in the back of the hood. Let your reaction kind of do its thing. After you're done heating it, you can take it off. Let most of those gases be sucked up into the hood system so that you aren't exposed to it. Okay? You'll then quench your reaction with cold water. You'll filter your product, and you're going to recrystallize it. At the end of all of that, you can get your melting point and a weight for your final product. Okay? The experiment works fairly well. The primary thing to be concerned about is the sulfuric and nitric acid. You are dealing with concentrated acids. Please, please, please be careful with those. Okay? Be aware of how much you're adding, where you're adding it, and who's around you when you're dealing with them. Okay? This lab, more than any other lab, causes burns. Okay? Usually at least one student per semester gets burned by one of these species in this experiment. Okay? Which brings up the next big point. Long pants are absolutely a requirement. If you do not show up wearing long pants, you will leave the lab, period. Okay? In other cases, we may have been slightly more lenient than necessary. This is one where there is no leniency. If you show up in shorts, you are not doing the lab, period. And that will count as an unexcused absence. Okay? So that's all I've got. If you got questions, please raise your hand.